All right, welcome to Turing Complete, a game in alpha or beta about building a computer from the simplest circuitry ever all the way up. It includes programming, logic, all of it. As a computer engineering student, this should be pretty fun. So let's go. All right, so we have a wire here connecting an input and an output. Looks like we can toggle that. So if I flip, oh, I can't toggle the output. I can toggle the input. So if I toggle the input, it's just a wire. It should also toggle the output off as well. Cool. Okay. We are not a plant. Okay. Okay, so we have to figure out what a NAND gate does. Well, a NAND gate is a not an AND gate. So it does the exact opposite of an AND gate. An AND gate only toggles on when both signals coming in are high. So two high signals outputs a low signal. So a not an AND gate is the opposite of that. So anything but two on signals. Cool. And we've unlocked an AND gate. Alrighty. So now we need to build a NOT gate with an AND gate. Well, that is easy. You take one signal and you tie it into both ends. So if this is off, right, these are both off. Remember that both two off signals on an AND gate are going to result in an on signal here. So off, on, it's one half of the NOT gate, right? And this is on, which means both these are on. That would be an AND, but this is a not an AND, so this will be off. So this should check. Cool. And we get a NOT gate. All right, now we get a NOR gate. All right, we have a NOR gate here, and what we need to do is build this with NANDs and a NOT gate. Okay, well, first thing we're going to do here, can we drop multiples of these? Yes, we can. All right, a NOR gate, we're going to first do that. And what is that? That is a NOT gate. So we're going to NOT both those. Okay, so we'll remove that. Go ahead and simplify this down. Take those away. So we're going to NOT both those signals. We're going to take that into here, into a NAND gate. And then we're going to NOT that as well. So this is an OR gate. We take both these signals, tie them in. Oop. Tie that, NOT that. We get an OR gate. And now we have access to an OR gate. Cool. Alrighty, so now we are building an OR gate. Alright, so a NOR gate, very simple to, an OR gate, very simple to a NOR gate. We don't have access to our NOR gate, so we have to use NANDs and NOTs. Well, we're going to need one NAND, and we're going to need two NOTs. We'll tie that out. So we have two knotted signals will become high here. These two high signals become a low signal because of NAND. That's how NAND works. Oh, and it shows you the logic here. So you can see how a NAND moves off, off, on. Okay, and if we have high, low, right? So then we have low, high, and low, high is going to result in this being on. That'll be on. Same goes for the opposite. And then both these on will both result in both these being off, and both off for an AND gate result in it being high. So that fulfills our truth table. And let's run it. And we check. Three components was... You cannot do that with less than three components. Don't let him fool you. That was a lie. The elephant is going to beat me. seating, a lot of paperwork. Okay. So we need to build an AND gate here using NAND and NOT. Remember what a NAND is? A NAND is a knotted AND. So if you knot a knot, it becomes a true. So we will knot that end. It is now true. And now we have access to an AND gate. Alrighty. Now we need the always on. We're going to do an always on. A fling florp. Okay. Alright, so an always on. If it's off, it's on. If it's on, it's on. So we can take an OR gate, right? Because it's going to take either OR signal. It doesn't matter if they're both on and this is on, as long as they're not both off. So then what we'll do is we'll throw a NOT on there. So we'll take the same signal, we'll NOT it, throw it in there, and if we'll take the regular signal and throw it in there. So if it's off, then this one's on, OR is good. If it's on, then this one's good. It'll go through. So, boom, cool. It's an on gate. Second tick. So it looks like from this truth table, what we're going to be doing is we only care about the second input. We only care about the second input. If the second input is on, no. We only care about the first input, and when the second input is not on. So if this is 0, 0, this is 1, this is 2 in binary, and 3. So 0, 1, 2, 3. We only care about 2 and not 3. Okay? So what we're going to do here is since we have an AND gate, we only care when input 1 is on and input 2 is off. So we have a situation here of you can do logical mathematics. Okay, so if you have, consider this A and B. If you have the only situation you need is true is when A is good and B is not, you have a situation where A on and B not. So A and B not. Knotted B. And this is the AND. We tie that to the out. We should be good. Cool. We unlocked a light bulb somehow? Okay. Was when we are at the second tick, this level builds a circuit that is green when we are at the second or the third tick. Okay, so this is an XOR gate. Also says that at the top. So, yep, we are doing an XOR gate. So this is only on when we have one on signal and not the other. These are really cool because you can use these to detect odd number signals. So what we're going to take here is we're going to take a couple AND gates and a couple NOT gates because we need two. We have two situations. Okay, so we'll take that and we'll go there. We want this to kind of look a little nice. There we go. That looks nice. And we'll take this guy and we'll go there. And then we'll go down there. We'll tie that together. But now we need a way to bring these two signals together, right? So we have A and not B, right? So this one. And then we have not A and B. So not A and B. Okay, so these are the only two situations we care about. We don't care about not A and not B or A and B. We don't care about those. We don't want those on. So we only want these two situations here. But we don't care which of these are, right? So it can be either or of these signals. So we'll OR them. I just made that look all sloppy. I don't have these spacing correct. Can I move this? Ha ha ha, I can. Okay, cool. So that should check. Nice, and now we have an XOR gate. So as we're going through here, we're unlocking each of these uh, separated things, which is kind of nice because then we get access to them later. So now we're building a bigger OR gate. So it's a 3-input OR gate. And look at this truth table. Don't let this get to you. A lot of it's all the same thing, right? So all we're taking here is we're making a 3-input OR gate. We can do this with two components. Two components. We have two inputs, right? So we take either or, A and B. So A or B. And we can take that. So either of those would pass through here. So this is the same thing. And then we just tie 3 in here. So we have A, B, C. So if A, B, or C goes through, we have 3. This big truth table, super easy. And now we have a bigger AND gate. So, okay. So this one, a little bit trickier, you think, right? Nope. Same situation. We're going to AND the 2 and then AND the other one. If I can get my wires to go together here, we'll make this look all nice. Can we? Nope, can't get those any closer. So, but yeah, you AND these two together, and you want that. So you only care the truth table if all 3 are on. Only situation they're all on. That's AND. So the only situation this works is if both these are on, and both these are on, and this one's only on if both these are on, and this one's on. So like you have to have all of them on. Otherwise, every condition fails. And now we get access to these. Wonder if we get like 4-input AND gates or OR gates. The inverse of an XOR gate, also known as an XNOR gate. Cool. Okay, so an XNOR gate. Truth table time. Okay, so this looks very close to the NAND gate, right? But we have both off, we're good, and both on, we're good. So this is the opposite of our NOR gate we're going through. So can we take a NOR gate and not it? We have our logic of our NOR gate. No. Logic of our XOR gate. There we go. So that logic, we almost messed up. So if we would have done a NOR gate, well, we'd have knotted it, we'd have ended up with a NAND gate. Right? Nope. We wouldn't have anything of that either. We'd end up with an OR gate. A NOR gate and an OR gate. And not. So we have situation 1, 2, 3, and 0 is false. 0 is true. 1, 2, 3 are false. So we take those away. What we want, match our truth table here. So we only care about situations 0 and 4. And this gives us 2 and 3, or 1 and 2, sorry. So 1 and 2, and this one, we knot those, we go through. I probably talked myself into confusion on this one, but an XNOR gate. It's one of those weird situations, but it's useful. And if you know how to use them, very good. So that, I think, will wrap up the first video, little tutorial here of basic logic of Turing complete. So this is pretty neat. This is a pretty fun game. Looks like they've got a lot that this goes into. I have to CPU architecture, mark this as a working computer. Some programming, CPU architecture, nice, nice, nice. Functions, I would think you'd want some of that in between there, but fine. And then assembly. So yeah, some of this seems a little bit out of order, but we'll see how they do it. If they're building upon things, that'll be pretty neat. But so that'll wrap up the first video, basic logic on Turing complete. Thanks for watching.